Welcome! Let's take a look at analyzing the behavior of the product of an exponential function with a polynomial. We will be looking for the intervals on which the function is increasing and decreasing, concave up and concave down, as well as locations of relative extrema and points of inflection. So let's go ahead and get started. To find the intervals where the function is increasing or decreasing, we need the first derivative. So f prime of x will be found using the product rule. The derivative of e to the x is e to the x. So derivative of the first times the second factor plus the derivative of the second factor, which is 2x, times the first factor. Notice that both terms have a common factor of e to the x. So we will factor that out and we will have x squared plus 2x minus 4 as the simplified form of our derivative. Now, we want to find the critical points of this function. The source of the critical points are twofold. The first source is where the derivative is equal to 0, and the second source is where the derivative does not exist. Now, looking at our function here, we have the product of an exponential, which is defined over all real numbers, and a polynomial. So there are no values of x for which this derivative does not exist. So we can say that there are no critical points from considering that case. So we will focus our efforts on identifying where the first derivative equals 0. That is e to the x times x squared plus 2x minus 4 equals 0. Now notice that e to the x is never equal to 0. So if our first derivative is going to equal 0, it will equal 0 because x squared plus 2x minus 4 is equal to 0. So let's consider x squared plus 2x minus 4 equals 0. Now that polynomial, that quadratic, does not factor. So let's use the quadratic formula. So x will equal the opposite of b, plus or minus b squared, or 2 squared, minus 4 times a, which is 1, and c, which is negative 4, all divided by 2 times a, which is 1. Simplifying that a little bit, x equals negative 2 plus or minus the square root of, now under our radical, we have 2 squared, which is 4, and then this second piece is equivalent to adding 16. So 4 plus 16 is 20, all over 2. Now, the 20 can be factored to be 4 times 5, and 4 is a perfect square. So we bring the 4 out of the radical, and we have negative 2 plus or minus 2 times the square root of 5, all divided by 2. I'm going to factor a 2 from my numerator. So I have 2 times negative 1 plus or minus the square root of 5, divided by 2. And the 2's will divide out. And so I end up with my critical points being negative 1 plus square root of 5 and negative 1 minus square root of 5. Now, as we do have 2 critical points, negative 1 plus square root of 5 and negative 1 minus square root of 5, this will divide the x-axis and the number line into 3 intervals. And we will be testing the derivative on each of those intervals. So the first interval will be from negative infinity up to negative 1 minus square root of 5. That is the smallest of the critical points. Then from negative 1 minus square root of 5 to the larger critical point, negative 1 plus square root of 5. And then our third interval will be from negative 1 plus square root of 5 onward to infinity. And so now we need to pick a representative point within each of these intervals to determine the sign of whether or not, whether the derivative is positive or negative. So in this first interval, I'm going to pick a number that's easy to work with. I'm going to go ahead and pick 10. That's a number that I know is safely within that interval, and it's relatively easy to work with. So f prime at negative 10 will equal e to the negative 10 times negative 10 squared plus 2 times negative 10 minus 4. And remember, all we're interested in here is whether this is a positive value or a negative value. So e to the negative 10, that will always be a positive value. Now, inside our parentheses here, we've got 100, which is positive, minus 20 minus 4. 100 minus 20 minus 4, 100 is much larger than the negative 20 and the negative 4, so we know that this number will be positive as well. And a positive times a positive is positive. So we know the derivative is positive in that interval. Now, choosing an x value in our second interval, 0 is safely within this interval. This is a negative 1 minus square root of 5 is negative. Negative 1 plus square root of 5 is positive, so 0 is somewhere in that interval. So let's check the derivative at x equals 0. We get e to the 0 times 0 squared plus 2 times 0 minus 4. Again, all we're interested in is the sign. E to the 0 is always positive. And in this second factor, 0 plus 0 minus 4, that's going to be negative. So we have a positive times a negative, which gives us a negative value. So the derivative is negative on that interval. Now we want to check our third interval. So choosing an x value that's within that interval, and that's relatively easy to work with. Let's go with f prime at 10. Then we have e to the 10 times 10 squared plus 2 times 10 minus 4. Again, we're only interested in the sign. E to the 10 will be positive. 10 squared plus 2 times 10 minus 4 will be positive as well. And a positive times a positive number is a positive number. So now we need to interpret the information we have. So looking for increasing and decreasing behavior, a function is increasing where the derivative is positive. So the function is increasing on this first interval, decreasing where the derivative is negative in the second interval, and increasing again in the third interval. So we can say that our function is increasing on the interval from negative infinity to negative 1 minus the square root of 5, union the interval from negative 1 plus the square root of 5 to positive infinity. we can say that our function is decreasing on the interval from -1 minus square root of 5 to -1 plus square root of 5. And so now we've determined the intervals on which our function is increasing and decreasing. Now it is possible from that to identify locations of relative extrema. Recall we had two critical points. One critical point was here at -1 minus square root of 5, and another critical point was here at -1 plus square root of 5. And we notice that at the critical point -1 minus square root of 5, our function changes from increasing behavior to decreasing behavior, which indicates by the first derivative test the existence of a relative maximum. We're going from increasing to decreasing. And then at our other critical point, at -1 plus square root of 5, we can see that our function is going from decreasing to increasing, and this indicates the presence of a relative minimum by the first derivative test. So let's go ahead and find the corresponding function values so that we can identify our relative extrema. So starting with f at -1 minus square root of 5, and evaluating our original function, we get e to the -1 minus square root of 5 times the quantity -1 minus square root of 5 squared minus 4. That's going to give us e to the -1 minus square root of 5 times, now we have to multiply using the distributive property, the -1 minus square root of 5 squared. Now, if you do that, you'll end up with 1 plus 2 square roots of 5 plus 5 minus 4. And if I simplify that, I'm going to get e to the -1 minus square root of 5 times 2 plus 2 square root of 5. So we can say that there is a relative maximum of e to the -1 minus square root of 5 times 2 plus 2 square root of 5. That's our maximum value at x equals -1 minus square root of 5. And that's by the first derivative test. Let's go ahead and look at our second critical point. Now we're looking at f at -1 plus square root of 5. So we have e to the -1 plus square root of 5 times -1 plus square root of 5 squared minus 4. And again, we'll have to use the distributive property to multiply out that -1 plus square root of 5. And when we do that, we get e to the -1 plus square root of 5 times, we'll have 1 minus 2 square roots of 5 plus 5, and then minus 4. Simplifying that, we get e to the -1 plus square root of 5 times 2 minus 2 square root of 5. So we can say that we have a relative minimum by the first derivative test of e to the -1 plus square root of 5 times 2 minus 2 square roots of 5, and that occurs at x equals -1 plus the square root of 5. So we've found the intervals for increasing and decreasing behavior and the locations of relative extrema. So now we need to move on and identify where the function is concave up and or down, and any points of inflection. We will be relying on our knowledge of the first derivative to help us with this.